In this video, we're going to start section 6.3. We're going to introduce the method of cylindrical shells. So this is often called also the shell method, colloquially, because it's easier to say than the method of cylindrical shells. But by introducing this method, it is an alternative to using the slicing method or the disc and washer method. And our objective is still the same with both of these methods. It's to find the volume of a solid of revolution. I have here, to illustrate how we set up the integral, I have a sample function curve that we're going to rotate about the y-axis. So what I'm highlighting right now is the actual curve that's going to bound a region in the first quadrant. And remember that we're going to actually revolve that around the y-axis, and that is going to create this solid of revolution that I have highlighted as using dotted lines. So this region right here, it's going to sweep out a solid that actually ends up looking kind of like a bundt cake. And so the strategy here is we're going to build up this volume not by taking these discs. So remember that with the disc method, what we would have done is we would have taken these horizontal rings and build up the volume that way. What here we end up doing is we're going to take an infinitesimal shell that's created by taking this rectangle and sweeping it out by revolving it about the y-axis. So this rectangle, which, as I'll discuss in a second, is infinitesimally thin, is actually going to give us this cylindrical shell. And we'll see as we sweep it out, we're going to take these infinitesimally thin shells and use them to build up the entirety of the volume. So now you can see that this is the cylindrical shell that's infinitely thin. Let's actually talk about how this is gonna. So the intuition here is that this thickness, which we're going to call dx, is the thickness of the shell. The height, of course, is also, it reaches from the x-axis to the function value, which is f of x. And what we'll see is we're actually going to end up using the formula for the infinitesimally thin cylindrical shell here. But before we get to that point, we do have to think about how to rigorize this, right? So one of the important skills that you develop in this class is to think about how the actual infinitesimally thin pieces are constructed from finitely many of them. So we're going to imagine that this is A and this is B, and so we're going to subdivide this interval from A to B into n regular subintervals. So this interval is going to be subdivided into n intervals of equal width. Delta x. From each, we then pick out a sample point. Oops, let's actually spell that correctly. X sub I star. And remember that the I subscript means that indexes which one of these subintervals we're talking about. So for instance, that x sub I would be located here, for instance. So there's n of them. Now, the infinitesimal shell that we're talking about here, right? If I may, I'm now going to rigorize this by talking about, if this is x sub I, then the width of that shell is going to be delta x, and the function height there is going to be f of x sub I star. So now we've attached it to an actual function value here and an actual number here, and the volume of this infinitesimal shell, so v sub I is, think about this rectangle being swept out, meaning we're going to rotate this and give it a full 2 pi rotation, and it's going to end up being 2 pi x sub I star y x sub I star. Well, that's the radius of this shell. And then we multiply that by the height and by the thickness of the cylindrical shell. And we know that the volume is approximated by the Riemann sum of these VI. So we're going to add these up, take the sum from I equals 1 to n of the V sub I, which ends up being this expression right here. So this summation, which is finite, keep in mind, is giving us the blueprint for our integral. For in the limit of the Riemann sum, so if we let n go to infinity, we end up with the volume is equal to the integral from a to b of 2 pi x times f of x dx. Okay, so not too bad. This is different from the formula that we obtained using the slicing method, and this reflects the fact that our infinitesimal piece here is the cylindrical shell. Let's see a basic example to see how this shell method is used. So we're going to use the shell method on the, we're going to find the volume of the solid generated by the region bounded by the curve y equals e to the minus x squared y equals 0 to the x-axis, and 0 between, x between 0 and 1, rotated about the y-axis. So remember that in the past, if we were using the slicing method, we would have had to reinterpret this region in terms of y, not in terms of x. But here then it actually becomes easier. So let me just draw the picture again here for you real quick. So it looks something like this. E to the minus x squared is also sometimes called a bell curve. It actually extends out infinitely. But since we're only going from 0 to 1, then it does not end up looking like an infinite bell curve. So this is my rough picture. And so remember that when we end up rotating it, it's going to end up looking kind of like this. All right. And so let's draw in our infinitesimal shell. I'm gonna be deliberate here and call it an infinitesimal shell, because fundamentally, even though I'm drawing in right now a rectangle, remember that we're going to sweep it out and it's going to make this shell shape. Okay, so crappy drawing aside, right, our infinitesimal shell that we're going to integrate is, remember, 2 pi x times the function value, which is e to the negative x squared, times dx. And again, this is the height, the thickness, and radius times rotation, or I'm just going to call it plus rotation. There are other ways of arranging this if you are not comfortable with this. So you can think about it in terms of the actual formula for a shell or some other way, but these pieces have to be all there together. So that means that our volume is going to be given by the integral from 0 to 1 of 2 pi x e to the minus x squared dx. Okay, now you may be wondering, what am I doing with this? Let's just go ahead and pause and reflect. The 2 pi can come out of the integral, and this buddy here in the exponential suggests that we can use the substitution rule. So we're going to let u be negative x squared, du is going to be negative 2x dx, and the x is there, right? So that's kind of the point here, that I'm going to end up replacing that x dx piece, this right here, using the du equation, right? And we can do even better, actually, because the 2 is there too. So that's going to take care of that as well. So to be clear, that means that 2x dx is going to equal negative du. And so everything that I've underlined inside the integral is going to be replaced. And then we just have to put negative du. All right? So that means our integral becomes the integral from, and the limits, I'm going to have to change those as well, but I'm going to get to that in a second. So pi e to the e to the u times negative du. And remember that we have to change the limits of integration as well. So 0 and 1, if we transform them, right, we're just gonna plug them in for x in this relationship right here. In other words, u of 0 is going to be 0, and u of 1 is going to be negative 1. So that's what our new limits of integration are going to be. And that way we don't have to revert back to substituting in x. All right, so all that aside, that means we end up with negative pi e to the u, evaluated from 0 to negative 1. And when we apply FTC2, this will become negative pi times e to the negative 1 minus e to the 0. And then simplify that, and you get pi times 1 minus 1 over e. And that's not too bad. So in the next video, whoops, that doesn't look good. In the next video, we're going to apply the method of cylindrical shells to more general situations. So the next video is pretty example driven, and then keep an eye on all the different